Welcome to EFSA's E-learning on uncertainty analysis. I'm Andy Hart, and this is the second of 3 presentations in the course. In the first presentation, we introduced key concepts and principles for uncertainty analysis, looked at a basic example on African swine fever, and explained why EFSA's guidance recommends using probability to quantify overall uncertainty. In this presentation, we look in more detail at the methods and options for basic uncertainty analysis using an example on Campylobacter. The key steps for a basic uncertainty analysis are to ensure assessment questions are well defined, include uncertainty analysis when planning the assessment, identify sources of uncertainty while doing the assessment, ensure draft conclusions are well defined, assess overall uncertainty for each conclusion, and report methods and results appropriately. Our example on Campylobacter is actually more than a basic uncertainty analysis, but extracts from it illustrate well these key steps which occur in both basic and refined uncertainty analysis. Let's start with the first step, ensuring assessment questions are well defined. Sometimes the terms of reference specify precise questions. In other cases, the terms of reference have to be interpreted to define the assessment questions, and this is a normal part of EFSA's work. These need to be well-defined scientific questions. Here are the terms of reference for EFSA's 2020 opinion on Campylobacter. EFSA was asked to identify possible control options for Campylobacter in broiler chickens and rank them in terms of their effectiveness for reducing the incidence of disease in consumers. And this is how that was interpreted in the opinion. In this case, the interpretation simply restates the terms of reference in the form of a question. In future, EFSA's framework on protocol development will require that assessment questions are defined in more detail. This is also necessary to enable the uncertainty of the answer to be assessed. EFSA's guidance on uncertainty analysis gives specific instructions for this. It says the assessment question should refer to an outcome or quantity that could, at least in principle, be observed in the real world or obtained from a defined scientific procedure, and it should specify the population, region, and time period of interest. So in the Campylobacter opinion, the assessment question was further defined for uncertainty analysis as follows. If the specified control option is implemented by all broiler producers in the EU that are not currently using it, what will be the percentage reduction in average annual incidence of Campylobacteriosis cases in the whole EU population, caused by Campylobacter species in broiler meat produced from chickens raised in the EU, other things being equal? This specifies the quantity of interest and the populations and regions to be considered, and implicitly defines the time period as that for which other things remain equal. The EFSA guidance also says, if the assessment question refers to a variable quantity, specify what summary of the variability is required, e.g. the average. This does apply to the Campylobacter example because the percentage reduction in cases will vary between years. So the question refers to the average. The next step in a basic uncertainty analysis is planning the assessment. It's important to emphasize that uncertainty analysis is not an add-on at the end of the assessment. It should start from the beginning when you're planning the assessment. You need to decide whether a basic uncertainty analysis is sufficient, assessing all the uncertainties together in a single step, or whether a refined uncertainty analysis is needed to assess some uncertainties separately before assessing overall uncertainty. If so, you need to decide which methods you will use for that. It's important to plan some meeting time to assess overall uncertainty and seek endorsement of your plan from the panel or unit before proceeding. EFSA's framework on protocol development will also require that future assessments are planned in more detail. When planning the Campylobacter assessment, the panel decided to use refined methods for some of the control options. Some options were assessed by modelling, which quantified uncertainty for some of the model parameters, and some sensitivity analysis was performed. And some options were assessed by statistical analysis of data from field trials, producing confidence intervals, which again quantify part of the uncertainty. For other control options, only literature evidence was available. Conclusions on these options were assessed by expert judgment, considering the combined impact of all the uncertainties in one step. So this is a basic uncertainty analysis. The next step is identifying sources of uncertainty. The guidance recommends to systematically examine all parts of every assessment to identify all sources of uncertainty that may affect the conclusion on the assessment question. That is, anything that might contribute to making the conclusion uncertain. The guidance distinguishes between uncertainties relating to assessment inputs and uncertainties relating to assessment methods, and both types must be taken into account. Uncertainties relating to assessment inputs include the relevance and reliability of data, data gaps, and the reliability of assumptions. Uncertainties relating to assessment methods include the realism of any models that are used and the rigour of methods used for literature search, statistical analysis, and expert judgment. For example, if the procedures used for searching the literature or expert judgment are simplified due to limits on time and resources. EFSA is increasingly using formal approaches with defined criteria for evaluating evidence, e.g. critical appraisal tools. These tools both identify and qualitatively evaluate sources of uncertainty affecting data or evidence. Here's an example from EFSA's 2019 opinion on setting dietary reference values for sodium, where they used colour coding to show the rating of the criteria for different studies. When using these tools, you also need to look for additional uncertainties they don't cover, including uncertainties associated with these assessment methods. If you're not using formal tools for evidence appraisal, then at minimum look for and list uncertainties affecting the assessment inputs and methods. The Campylobacter opinion goes beyond a simple list of uncertainties. It contains two tables listing strengths and uncertainties affecting studies used in the assessment, and another table summarising how different types of uncertainty affect the ranking of control options. In summary, the key messages are: identify uncertainties affecting the evidence and methods used in the assessment, and document them in a way that will be helpful when assessing their combined impact on the conclusions. The next step in a basic uncertainty analysis is ensuring conclusions are well defined. This comes when you are starting to draw conclusions from the assessment. It is important they are well defined to make the meaning of the conclusion clear and to enable its uncertainty to be properly assessed. The requirements for well-defined conclusions are the same as for assessment questions, which we saw earlier. In the Campylobacter opinion, the conclusion for each control option is an estimate of its effectiveness. This estimate is defined by the assessment question, which, as we saw earlier, specifies the quantity to be estimated and the population's region and time period to be considered. The next step in basic uncertainty analysis is to assess overall uncertainty. EFSA's guidance says that assessors must characterise the overall impact of the identified uncertainties on the assessment conclusion in a clear and unambiguous way. This is a mandatory requirement for all assessments to comply with EFSA's principles on transparency and to ensure EFSA's assessment of the uncertainty can be clearly understood by risk managers. Note that this recommendation refers to the overall impact of the identified uncertainties. The guidance refers to this as the overall uncertainty, which it defines as the assessor's uncertainty about the question or quantity of interest at the time of reporting, taking account of the combined effect of all sources of uncertainty identified by the assessors as being relevant to the assessment. Note that this definition refers to your uncertainty at the time of reporting, recognizing that your uncertainty might change if you had more time or obtained more information. Also, it makes clear that you should focus on the uncertainties you can identify. You're not being asked to assess uncertainties you don't know about, the so-called unknown unknowns. The guidance also recommends that assessors express in quantitative terms the combined impact of as many as possible of the identified uncertainties, and that assessors should always try to express uncertainty of conclusions quantitatively using probability. The guidance recommends using probability because it has defined meaning based on comparisons to well-understood standards such as tossing a coin, rolling a dice, or taking balls from an urn, as we saw in the first presentation, whereas qualitative expressions of uncertainty or confidence are ambiguous and interpreted differently by different people. Overall uncertainty must always be assessed by expert judgment. This applies to every assessment because even when you're using data or models to quantify uncertainty, there are always additional uncertainties that need to be taken into account. Of course, this must be based on evidence and reasoning, and expert judgments are subjective, so it is important to make them well and guard against bias. EFSA guidance provides structured methods for this. EFSA has a separate guidance document on expert knowledge elicitation, or EKE, but these methods are very formal and time-consuming. So the uncertainty guidance describes semi-formal approaches which can be carried out within the normal activities of a working group. Let's go through the basic steps of a semi-formal expert knowledge elicitation, or EKE, and look at some examples. The first step is to check the conclusion or estimate to be considered is well defined. We've already done that for Campylobacter. The next step is to decide how the overall uncertainty will be expressed. For a conclusion, this can be a probability or approximate probability. We saw an example of this in the first presentation from the opinion on African swine fever, where a range of probabilities was used to quantify uncertainty about whether the disease will spread. Where the conclusion is an estimate of something, you can use either a full probability distribution or just a probability for a specified range of values. This applies to the Campylobacter example, where the conclusion requires an estimate of the percentage reduction in cases of the disease if a control option is implemented. A probability distribution quantifies the range and probability of possible values. The width of the distribution shows the range of values that are plausible for the estimate, in this case the percentage reduction in cases, and the vertical axis shows the probability of different values within that range. The true value is judged most likely to be in this region, less likely to be in this region, and virtually no probability here. Note that there is only one true value. The distribution represents uncertainty about that value, not variability. We generally use 5 judgments to elicit a full distribution: the lower and upper plausible bounds, then the median, and finally the lower and upper quartiles. It's done in that order to reduce the risk of bias. In some cases, it may be sufficient to elicit a single probability for whether the quantity of interest is above or below a given value. For example, the probability of exceeding a conservative estimate. This is called a probability bound. The probability could be precise or approximate, and the uncertainty guidance contains a harmonized scale of approximate probabilities that may help the experts to consider what range of probabilities is appropriate for their assessment. In the Campylobacter opinion, it was decided to express overall uncertainty using full probability distributions. The next step in a semi-formal EKI is to decide which experts will participate. You need to consider what expertise is needed and choose the experts accordingly. This may include some or all of the experts in the working group, plus additional experts if needed. In the Campylobacter opinion, it was decided that all the working group members would participate in the judgments. Next, plan the process for making the judgments. It's generally recommended to make the judgments in 2 rounds. First, each expert makes their own judgment, and then these are shared and discussed, and finally, the group develops consensus judgments. This will produce better judgments with less risk of bias than going directly to a group judgment. Next, summarize the evidence and list the uncertainties. For the Campylobacter opinion, this was done using the tables which I showed you earlier on. The final steps are to elicit the required judgments or distributions and document the rationale, that is, the evidence and reasoning for those judgments. This graph shows the results of 2 rounds of elicitation, assessing overall uncertainty for one of the control options for Campylobacter, discontinued thinning. The distributions with dashed lines are fitted to the individual judgments of the 9 experts, and the solid curve is the consensus distribution agreed by the experts as a group. The experts summarized the evidence and reasoning for their consensus judgments in a table in the opinion to make the basis for their conclusions transparent. The EKI process was repeated for 8 control options, and the results were presented together as box plots, enabling comparisons between the control options. Here is the box plot for the control option of discontinued thinning, from the consensus distribution I showed in the earlier slide. The uncertainty analysis for this was a basic one. Overall uncertainty was assessed directly by expert judgment based on evidence from the literature without quantifying any parts of the uncertainty separately first. That also applied to the control option designated tools per broiler house. For the other control options, some uncertainties were quantified by modelling or by statistical analysis, and the results of that were then used as a starting point when assessing the overall uncertainty by expert judgment, a refined uncertainty analysis. We'll look at an example of that from plant health in detail in the next presentation. Of course, if an opinion produces many estimates, as in this case, or produces many conclusions, it will be impractical to carry out the full semi-formal EKI process for all of them. So a key lesson learned during the implementation of the guidance is that there will often be a need to prioritize or group the conclusions or estimates arising from the assessment and/or simplify the EKI process so that overall uncertainty can be assessed efficiently within the time and resources available. Let's have a look at some options for prioritizing and grouping. The first option is to focus more effort on the most important conclusions or estimates. This means giving priority to those that directly address the terms of reference, plus others that are likely to influence risk management. The next option is to group conclusions or estimates affected by similar uncertainties. For example, if you have estimates of the same quantity for multiple populations, assess overall uncertainty for one and use it as a starting point for simplified assessment of the others. Another option is to assess some conclusions or estimates collectively, if appropriate. For example, assess the probability that all the conclusions are true, or that all the estimates are below a critical threshold. You can also simplify the EKI process itself Here are some options you could consider. You can elicit probability bounds rather than full distributions for estimates, reducing the number of judgments required for each estimate from 5 to 1. You can use the approximate probability scale, which may make the judgments easier for the experts. For an estimate, you could show experts the average distribution as well as their individual distributions to help, but not determine, the consensus judgment. This was done in the Campylobacter assessment. You can elicit consensus judgments directly without first eliciting individual judgments, or ask a subset of the experts to propose a consensus judgment for acceptance or revision by the group. If necessary, this subset could be only 1 or 2 experts. Finally, as a worst case, you could omit uncertainty analysis for the least important estimates or conclusions. The first 2 options in the list are good and are described in the guidance on uncertainty. The third, fourth and fifth options are based on experience so far and are not yet in any published guidance. They will reduce the quality of the judgments or the protection against bias to some extent, so you need to think carefully about the trade-off between simplifying and the quality and rigor of results. The last option means not applying the guidance to some conclusions at all and should be avoided as far as possible. If you need help to decide what is appropriate and proportionate for your assessment, or help to conduct the EKI, specialist support is available within EFSA. The final step of a basic uncertainty analysis is to report the methods and results. You should do this in the same way as other parts of the assessment, and report each conclusion with your quantitative expression of its overall uncertainty. In the Campylobacter opinion, median estimates and 90% probability intervals quantifying uncertainty were reported in the conclusions summary and abstract, together with a qualitative statement that the rank order of the options was uncertain due to the large overlap between the probability intervals. If there are some uncertainties that you feel unable to include in your quantitative assessment, you must describe these qualitatively and state what assumptions have been made about them. This is essential because your probabilities will be conditional on those assumptions being correct. Finally, if legislation or risk managers require firm conclusions, define the level of certainty required for them, as we discussed in the previous presentation. So in this presentation, we have focused on basic uncertainty analysis. We've looked in detail at each of the key steps, illustrated by examples from the Campylobacter opinion, and we've discussed how the assessment of overall uncertainty can be adapted to fit within the time available. In the final presentation, we will explore some of the options for refined uncertainty analysis, where some uncertainties are quantified separately from others before assessing overall uncertainty. And we will use an example from the Plant Health Panel to show how this can be both feasible and helpful.